our vision here in our collaboration, and I'll put up the team members at the end, but it's basically myself, Tom Purdy, who's here at Pitt, and David Pecker, who's a theorist at Pitt, and Jake Taylor at Maryland. And our vision is also with the magnetic trap that you just heard about. Well, that's a long story of how we got there, but essentially that's what we're doing now. And we want to trap these diamonds in the trap. We want to create the superpositions that you just learned, and we expect there should be long coherence times, but that's something we really want to measure. We have several ideas for this coming courtesy of our theory colleagues. And of course, the reason that we think all this is doable is because we have our NV qubit that you learned about in the last talk as well, and all the cooling and trapping techniques from atomic and optical physics. And of course, this was all motivated by several theoretical proposals to couple and create superpositions of the translational modes. We wrote one also for the rotational trapping as well. And so let me move on. So what's the basic idea? Well, you're all familiar, so I can go quickly through this. We want to levitate a diamond crystal with at least one high coherence spin. We want to prepare both the motion and the spin in a low entropy state. We want to induce an entangled state that helps us to probe the coherence properties of both systems. And the ingredients, I'll just quickly go over them: materials, trap, optics, microwaves, all brought together, optically detected magnetic resonance, and mechanical measurement. We'll talk about some of this in my talk today. And then the theory, as I just mentioned, to connect entanglement and coherence and the measurements. Okay, I'll go quickly. Don't need to say too much. NV centers, I think everyone is familiar. We have access to optical readout of the spin state, which is what enables a lot of this and allows us also to prepare the pure spin state. We know that in bulk diamond, we can get long coherence times, and you just heard about this very nice work from the Warwick group on doing that in nanodiamonds as well. And another resource of the nuclear spins, something that Jake and collaborators are exploring of how to use that as well for our mechanical coherence measurements. And so there were some questions about magnetic trapping, and this is something that we did. That is, we took permanent magnets, we put them in this magnetic pole pieces, or high susceptibility pole pieces, and this is a rendering of the trap. Typical gaps that we can control, shown here, that we have demonstrated. Magnetic gradients in our current, somewhat not optimized trap is on the order of 10 to the 3 Tesla per meter. Here's a potential energy for the trap. You can see it's a combination of the diamagnetic susceptibility for the diamond particle and the gravitational interaction with the mass of the diamond. That's what leads over here to three-dimensional trapping. This is just illustration of our experimental setup. We load the particles in with a piezo-driven shaker, and we can apply feedback cooling, which I'll show you in a second. We use the green laser for like NV excitation and also detection. In this old drawing, we are now improving that as well as part of this grant. So here's an image of our magnetic trap with a diamond, and these are like typical images of the micro diamonds that we've been using, which are just commercial. We don't have access to these beautiful diamonds that Gavin was showing, although I think we can certainly discuss some collaborations there. Yeah, we are not quite ready. We want them, but maybe not quite ready yet for the most beautiful ones. And here's the feedback cooling applied, which shows how we go from room temperature oscillations down to a cooled mode of the motion. This is in vacuum. And the PL spectrum of the NV center with that bright spot in the center. That PL spectrum is a smoking gun, I guess, in some sense, that there are NV centers. And we can also do measurements of the temperature of the center of mass motion using the displacement sensing, and I'll talk about that in a little bit. We haven't quite gotten to the nice 300 millikelvin result. I'm definitely interested in talking to you, David, about how you achieved that. We would like to improve this as well in our current system. But one of the things that we were worried about, because this had been my experience with the optical traps, just like Gavin mentioned, we were concerned about the heating of the crystal. So one of the measurements that we did, we used a well-known physics of the NV center, which a defect which is in a crystal, the ZPL over the total emission is for temperatures which are far less than the Debye temperature of diamond, is basically goes as T cubed, where T is the temperature. This was shown in this paper a while ago, so that just means we take PL spectra and we look at the zero phonon line and we measure the integrated area under that ZPL versus the total emission. And we can calibrate that. So the inset here shows the calibration on a heated plate first. We took diamonds, put them on a heated plate. We can change the temperature and measure this T cubed dependence. And then the data points in the main figure show, as a function of green laser power that we apply to the diamond, that we can indeed see that the temperature remains stable in our magnetic trap. So this was an important step for us because we really wanted to convince ourselves that we're not just going to heat the diamonds as we increase the green laser power. We have done spin resonance. Unfortunately, the diamond crystals, I'll go back again to the diamond crystals, the material that we had was not great in terms of the coherence or properties of the NV center. We had trouble with the ODMR signals even outside the trap, but we were successful in getting some ODMR signal from these diamonds. So that's an encouraging result, I would say, at this point. We're still a long way away from doing the beautiful coherence type measurements that we want to do in the trap, but that will hopefully happen as part of this grant, which will be a step in the direction. The next thing I want to tell you the project is a question that Tom Purdy has been thinking about very deeply, which is we have these dielectric scatterers, which are quite unlike. Somebody else raised this question of like, oh, these are these shards rather than nice spheres. And although people in the levitated optomechanics community have thought a lot about scattering from dielectric particles that are subwavelength, these particles, as you already saw, are very, weird shaped, and they can give rise to scattering that's different. And so we want to come up with a measurement scheme that's high detection efficiency, low measurement imprecision, and that was the goal. And so Tom has come up with this, Tom and his students have come up with this very nice theory based on the information radiation pattern that is normally used to tell you if you have scattering from a subwavelength particle, then you really want to look in a direction, in these directions. So this is information radiation, not the electric field pattern of the dipole, but this is the directions in which you get the maximum information about the movement of the particle. And that has already been known for some time by a group of Lucas Novotny, I think. But what Tom and his students figured out is that if you now think about if you want to detect this on a quadrant photodiode, for example, which is a standard technique in optical measurement. What happens is that if you add up the contributions of each of the individual area elements in the detector, then there are contribution from the signal that comes from the scattered field and the input laser weighted by each area element on the detector minus the noise also from the short noise, basically. And so this differential area or differential detection efficiency can actually have regions that are detrimental to the overall detection efficiency. That's the negative part in that. We can see it a little bit more clearly here. So those regions which are marked in red are actually negative. So they contribute badly to or they reduce the detection efficiency. So in fact, if you cut them out from the quadrant photo detector, you can actually improve the overall detection efficiency. And the nice thing about this scheme and this approach is that it gives us a sort of empirical way to determine the best sort of detection scheme, and that's demonstrated by this experimental, this is the theory, which shows if you start with a block that is 0, which means basically the whole quadrant photodiode, then this is the efficiency over here in the two different directions, x and y. But now if you include a block with different angle, the angle is just what is subtended at the detector, then you can see that the efficiency actually improves, and it improves at different block angles for x and y separately. Okay, that's the theory, and this is an experiment. I don't have time to go through all the details. I'm sure some of you might have been at Tom's poster earlier, and you can talk to him more about this. But they started with a silicon nitride membrane, used the block, and then they scanned another probe to measure the contribution of the efficiency from individual parts of the detector. And I'm just going to go over this quickly. So here's the position of the wire, here's the ideal pattern, here's the differential detection efficiency, and then once you block the central region, basically you get an improvement in the efficiency. And that last plot over there is sort of the equivalent of the theory plot, where you see the actual increase in the detection efficiency that they predicted. So that's Tom's result, which is very nice. And will hopefully, as we now start to do not just cantilevers, but we start to put in our diamonds, we can actually use that technique to improve our detection efficiency. So what, now we step back a little and think, this is the theory part of our collaboration has been thinking about what things that are really enabled by our approach. And one of the very interesting things about these magnetic traps is that they are low frequency, low mass, and large gradient, which produces a very large quantum coupling. And so the magnitude of the quantum coupling, which is about 1 kilohertz, even in the traps that we right now have, and which we will improve as part of this grant. So we could approach several kilohertz quite easily, which is much larger than the frequency of the mechanical modes, and is approaching sort of the coherence times, for example, of the best diamonds that we have just heard about. So this, of course, is one of the reasons that we think that this will be very useful for these macroscopic quantum superpositions. And it, in fact, suggests you can get a harmonic oscillator lens during the macroscopic superposition that's many, many times the harmonic oscillator ground state wave function. So we anticipate we can entangle the spin and the motion if the mechanical coherence is long enough, but this is something that we want to measure. And for this purpose, Jake and his postdoc have a paper out on the archive for an entanglement witness that we can measure that will allow us to actually find this mechanical decoherence, and they have a scheme for doing this. But also, and this is the last part that I want to tell you about, it suggests a potentially novel readout for the mechanical motion, which will include the ability to now detect forces at a very high sensitivity. And of course, and the problem is sort of this Humpty Dumpty that people are talking about is the spin causes a substantial back action on the mass because this coupling is so strong, right? And so we have to worry about this. So for example, we already heard that you can do Ramsey fringes or you can do echoes and so on. And these are things that we have done in my lab many times and many other NV labs around the world, where we can do Ramsey fringe and we can use that to measure the external magnetic field. In this case, this external magnetic field comes from the motion of the particle in the gradient of the trap. And these are just some experiments that we've done in the past. So if you think about what's going on with the diamond during this sequence, so the top one shows the Ramsey sequence. You start out, you create a superposition after the first pi/2 pulse, and that evolves the position. As you can see, the two arms of the interferometer, if you like, in this case, are going to be separated in their position, which means that when you do the measurement of the spin, you're going to have back action on x, but also on v. You could also draw the same thing for the velocity. It will be linear during that time because of the force created by the Stern-Gerlach setup. The same thing now with an echo sequence, which is a standard, again, technique that we all do in our labs for NV sensing. And now you can see here that we turn around the velocity, but the position is still separated, which means there'll be back action on this mechanical motion. But the back action will be in x only, but the v back action will be removed. So finally, we can do the car-per-cell sequence, and this has the nice property that within the sequence, we can just follow it through, and you see we get back, in principle, 0, of course, not quite, back action on both x and v during this sequence. So this, with this idea, you can now ask yourself, if you have forces that are on the time scale of this sequence of the length between the pi/2 and the pi pulses, what would be, how sensitive would you be in these sequences to those forces? And this is what Jake and his postdoc have been working on, and you can see these nice graphs here. On the first plot, these are the parameters. You can see these are fairly conservative, we believe, parameters for all the numbers, and we can already see that we are getting down to tens of yoctonewtons sensitivity with optimized coupling and number of spins in the in the particle. And with that, we can also look at the range of frequencies. As you can see, we are starting in a situation where the trap above the trap frequency, and as we get to higher frequencies, the noise floor descends, and then after certain point you get aliasing due to matching of the multiple periods of the force within the trap. Okay, that is pretty much, I'm done, but I'll just conclude with acknowledging, with a summary of what we have done, and outlook, which is, some of this is just very practical. We want to improve lots of things on the trap and the cooling, as well as the ODMR contrast, which we'll hopefully talk with Gavin and other people about, and get to better vacuums. But I do want to not forget this slide where I acknowledge all the people who are working on this project and have contributed to all this cool work. And we are very grateful to this funding, and I will make sure the next time this slide is put up that I acknowledge the other other agencies as well. Thanks for telling us about that. Okay, thank you.